Well, good morning. It's a pleasure to be here, and for me personally, it's always great to be in a room full of people that I don't need to convince that nutrition is important. The only disclosure I have to make is that I work for the government, which means literally I'm not allowed to have anything to disclose. So I start with a picture of the International Space Station here. Dr. Douglas did a great job of giving the food preamble, and I usually start with the space station to make the point that, a lot of people out there seem to believe that NASA closed shop when we retired the shuttle 8 years ago. But the reality is that we've been quite busy, and the space station is an incredible engineering feat. And the space station also represents a little over 18 and a half years now of continuous American presence off the planet. Today's been a big day in terms of current events. Anybody know what happened today in the last 24 hours? There you go. Thank you very much. The crew returned. So the 59th expedition to the International Space Station landed in Kazakhstan. This picture is not from this morning's landing. Actually, it was late last night. But this is about what it looks like. The crews I've heard talk about it will say something like it's the equivalent of several explosions followed by a car crash. That they do bang down in Kazakhstan. The flash you can see there is actually the retro rockets firing, which is an attempt to slow that vehicle down a little bit more before it touches down or slams down onto Earth. About a third of the time, I'm told the capsule will actually land in the proper orientation. A lot of times, if it's not exactly horizontal, it will shoot off to the side, and you end up banging and rolling, and it's a little bit of a ride. The crew right now is on their way back. They pick them up, and the search and rescue teams find them, do some quick medical checks, put them in a helicopter, flying back to the nearest airport, and then we put them on a jet, and they're on their way back to Houston. Right now, they're probably somewhere over the Atlantic. Just to give you an idea of where we are. So I lead the Nutritional Biochemistry Lab at JSC, and as Dr. Douglas said, our job is to come up with the nutritional requirements, and it's her job to come up with a food system that meets those requirements. And I'm actually very proud in a very dorky way to tell you that this is our logo. You are the first people to see that. That is the first time that logo's seen the light of day. We had a logo that we created thank you. We had a logo that we created 20-some years ago that had the shuttle on it, and I was told it was out of date. So with tremendous effort, we came up with a new logo, and just to give you an idea of how compulsive we are, where am I, the pointer? Over here we have an artistic license vitamin D molecule. We've got some collagen crosslinks in there, which we've done a lot of work with that. We've got your DNA, and we've got one black spot there to denote that we've done a lot of work looking at one carbon metabolism. So that you would not believe what it takes to make a logo, nonetheless. So again, our goal is to determine the nutritional requirements for spaceflight. And I often hearken back to, as Dr. Douglas did, that when we look at history, history has taught us many ways how nutrition either made or broke many an exploration mission. And scurvy is the big one that realize scurvy killed more sailors than all other causes of death combined. And that on those 3 or 4 month missions, that was a huge deal. And again, as you've heard, on a 3-year mission to Mars, there's not a nutrient we can run out of that is not likely to end in a very bad way. So that is sort of the backdrop in which we work. So as we try to build nutritional requirements, we need to also take into account the fact that nutrition interacts with literally every system in your body. And then we also need to take into account the spaceflight unique elements, things like confinement, distance from home, stress, the limited food system, radiation. All of that compiles onto the human and strains the system, if you will. And as we look at nutritional requirements, we need to appreciate the fact that the nutritional requirements on Earth, the DRIs, if you will, are built to stave off deficiency. And while we need to stave off deficiency, what we're really trying to do is to prevent disease. So we're not worried about those individual systems. What we're worried about is trying to prevent things like cancer and osteoporosis and atherosclerosis. And as you know, the DRIs at this point don't do that. And that is the job that we have of trying to look at, okay, we're going to send people out to Mars. what do we feed them? And while we're a long way off from going to Mars, the people like Grace need to know those limitations so that they can go build the food system, because these things don't happen quickly. Okay? So the work in our lab breaks down to two different elements. We do what we call operational work, which is essentially clinical work that we do for the flight surgeons, which is keeping astronauts healthy. We do a nutritional assessment profile that we collect blood and urine before and after flight, and we do a broad swath biochemical analysis and provide a report to the flight surgeon of making sure that the crews are healthy from a nutrition perspective when we send them up there and when they get back. So as I mentioned, Anne McLean, the U.S. astronaut, and David St. Jacques, the Canadian astronaut, are in a plane on the way back to Houston. They'll get in, I haven't checked the exact time, but it'll be around 11 o'clock or midnight tonight. And my team will be there to meet them quickly with a needle to get some blood so we can go off and start running those tests. And just to show you how mean we are, we actually put a cooler with bottles in it on the plane that they're flying on, so they have already started their 48-hour urine collection for us. While the crews are on orbit, we do track two different things. We track body mass with a very exotic device here in the middle. You see Karen Nyberg on it. This is the Space Linear Acceleration mass measuring device. And as the name implies, what happens is you climb onto it. It's about 8 to 10 inches away from the wall. You hold on tight, you push a button, it pulls you towards the wall with a known force. It measures your acceleration. And by using the physics of force equals mass times acceleration, you can determine the body mass. Costs a little more than a scale you'd find at Walmart. But when you think about it, being able to track body mass on long duration missions is one of the most critical elements. When you go to the doctor's office, the first thing they do is put you on a scale. That's not an accident. So having access to this is extremely important. The other thing we do is we track dietary intake. A couple of years ago, we built an iPad app that we developed for use on space station. You can see it here. This is our old logo on it, which we were very proud of. We were very excited that it was on there. And here you can see Peggy Whitson with the iPad, with the app in her hands. This is, again, it's a way to track dietary intake. And you can imagine that not every astronaut is excited when we sit down with them ahead of time and say, look, we want you to check, we want you to record every single thing you eat for the next 6 months. But they do phenomenally well with this thing. And I think a lot of that is a tribute to the fact that the app is incredibly easy to use. It's incredibly user-friendly, and it provides them real-time data. And as you've heard, one of the biggest things we drive to the crews is that you've got to eat. You've got to maintain your body mass, and that if you're not getting enough calories, if you're losing body mass, everything else falls out of place. You lose more bone, you lose more muscle, your cardiovascular system doesn't like it, oxidative stress goes up, that you've got to eat. So we spend a lot of our time doing that. Operationally, we do provide inputs to future space programs. So this is a cartoon diagram of the Orion vehicle that you can see over here, which is the vehicle that will launch from Earth that will take crews around the moon. And then on the right is what we call Gateway, which is a mini space station, if you will, that is in the planning for orbiting the moon. And we will send crews up there to spend, right now they're talking about 30 to 60-day missions on that vehicle. And I will be the first one to tell you that I am as far from a rocket scientist as can possibly be. And you might be wondering what nutrition has to do with planning these vehicles. We've had a lot of things that have come up lately, just to give you an idea of how much fun my job is. Grace and I have spent a lot of times in meetings over the last several weeks because the amount of food we wanted to fly for these missions was based on essentially DRI equations for energy requirements for an average astronaut. And we got pushback from the vehicle, and we got pushback from the astronaut office that they wanted to send less food. Okay? Food takes a lot of space, food takes a lot of mass. So we literally find ourselves fighting to keep food on the vehicle. Okay? On a bit of a darker element, we just had one. NASA's always very big on planning for contingencies. Okay? And one of the contingencies I just got called on is for Gateway missions, which is if that vehicle docks and you've got a crew on Gateway and there's something wrong with that vehicle and the crew can't get home, how long can you keep the crew alive? So you get into things like how many calories do you need to feed somebody to keep them alive, and for how long? And then the engineers balance food with water, with oxygen, with CO2 removal, and build for how quickly do they have to have another vehicle on Earth to get up there to get the crew and bring them home. And so we spend a lot of time reading Ansel Keys' starvation literature, which isn't exactly right, because we're not talking about starving them, we're talking about giving them something. The trouble is nobody's done a study of, well, what happens if I give you 200 calories a day? What happens if I give you 400 calories a day? So we end up trying to do our best to read the tea leaves in the literature to come away with those answers. For the sake of time, I'll skip. There's another contingency we've been working on. If there's a shortage of questions, you can ask me about that, because that one's a little more bizarre. And we do a lot of research as well. So we do operational work and we do research. The research we do is competed. We fight for funding with people across the nation. We write proposals and scratch and claw just like everybody else. And one of the things we often do is look at ground analogs. Are there ways that we can simulate things on Earth to help us understand changes during flight? So we will do things like put people to bed in bed rest studies for weeks, months, to look at how they adapt and look at how countermeasures can work to help mitigate the negative effects on the body. Dr. Douglas talked about the chamber studies we do. We've done studies with folks at the bottom of the ocean for a couple of weeks because the increase in oxidative stress changes iron metabolism, changes red blood cell metabolism, changes folate metabolism. So while they're doing studies of other things, we look at what that means to nutrition. And then we've done work in the Antarctic, not on penguins, but on people wintering over, because it's a great place to simulate vitamin D in people that don't see sunlight for 6 months on end, to try to figure out how much vitamin D you need when there's absolutely no external contribution. So the ground research we do is obviously relatively exotic, but nothing beats flight research. We've had some tremendous opportunities over the last 12 or so years to do research, and as I always tell people, our research boils down to blood and urine, which is not the most exciting things people want to hear about, but it is what it is. A couple of pictures here. You can see Luca Parmitano drawing blood from Karen Nyberg, Nicole Stott centrifuging the blood. You don't often see a centrifuge in the wall, but it works. That's one of the benefits of working in zero gravity. Sunny Williams is one of the few crew members who was nice enough to take a picture of her urine collection device. We don't get many pictures of that, and not hard to imagine why. I don't know if you can make that out, but the UCD is down there. It's in a Ziploc bag like it's supposed to be. There was a different crew member who took the UCD out and took a picture of it floating, which I thought was really cool. Which again tells you a lot about me. But you can imagine the safety folks at NASA were not too excited to see that thing floating around. We've collected urine on, I think, 65 astronauts during spaceflight, and I will tell you, not one of them came back and said, wow, that's a great way to collect urine. And we did this typically on a 6-month mission. We'd collect urine 5 days, so 5 24-hour pools. They'd collect each void into one of those devices. And if you read some of the books astronauts have written on the way back, there are literally a 1.5 to 2-page descriptions of just how awkward, painful, and disgusting it is to collect urine during flight. But it's a living. We have a minus 96 degree freezer, so you can see the smoke coming off there with Chris Cassidy. And then we used to bring samples back on the shuttle. When the shuttle retired, we were left waiting for Elon Musk's SpaceX vehicle, because that cargo vehicle is the only one that comes back to Earth. There's a number of cargo vehicles that bring stuff up to space station. Most of them burn up coming through the atmosphere, so they'll fill them up with trash and essentially throw them away. SpaceX is the only one that comes back. It splashes down in the ocean, and then Elon pulls it out of the water, and we get the freezers out of there, and we get our samples back. We've done a fair amount of work. I don't have a lot of time to talk near about all of it, but we've done a lot of work with diet as related to bone. And again, very briskly, we've shown that omega-3 fatty acid intake is beneficial for bone. We did bed rest studies where we showed that. We did cell culture studies where we showed that. And literally from a crude food frequency questionnaire that we had at the time, we showed that crew members that ate more fish lost less bone. Okay. We've done some studies looking at fruits and vegetables and acid-base balance, showing that if your diet is more basic or basogenic, if you will, that is beneficial for bone. Our colleagues over in Germany, Martina here, has done a number of studies showing that sodium is bad for lots of things, but sodium in particular is bad for bone. That high salt intakes will antagonize the bone loss of spaceflight. And we also published a study a couple years ago showing that iron did the same thing, that high iron stores in the body will be detrimental to bone health. Okay. Grace talked about the fact that we just finished a 45-day chamber study where we answered the very basic question of, if you feed people better, will their physiological outcomes be better? And we're still cranking the samples and the data from that. And then the next stage of that experiment is in the early days of, we're going to do the same thing in flight. If we fly better foods for crews with more fruits and vegetables, more sources of omega-3 fatty acids, can we mitigate some of these negative effects of flight? And somewhat briskly, the most incredible thing I've seen in the research that we've done over the years comes with eye research. And about a decade ago, we realized that astronauts were coming back to Earth with changes in their eyes. Okay, there's some nuance to it, it's complicated, but changes to the back of the eye or the retina. So we see things like optic disc edema, choroidal folds, cotton wool spots. We've seen some globe flattening and changes in refraction in some crew members. Okay, and it's very important to remember, it's not everybody. The incidence is debated and the numbers are all over the map, but the most recent I've seen is that about 18 to 20% of crews come back with optic disc edema, swelling of the area where the optic nerve comes into the back of the eye. Okay. When this came up, again, about 10 years ago, we went to the flight surgeons and said, look, we've got a lot of biochemistry data on astronauts. Why don't you tell us who had eye issues and who didn't, and we'll see if maybe we've got some data that can help you. And they wouldn't. And I think nobody said it out loud to me, but I think the assumption was, well, you're a nutritionist. What do you know about eyes? And long story short, we were put in a position where we could break the code, and I talked to my colleague Sarah Zwart and said, break the code. I will take the blame in the fall. I'm directing you to break the code and see what we've got. And one of the things we had looked at was one-carbon metabolism. We looked at homocysteine as a marker of folate status and B12 status, as again, I think this group appreciates more than any other group I've stood in front of. I would say everybody hates biochemistry, and the problem is it matters. So when I sent Sarah off to look at this, I could tell you literally the day, the date, and the hour. She came back into my office and said, there's something going on with one-carbon metabolism. Okay? And what she had found, very simply, was that the astronauts that had eye issues, which are shown here in the yellow line, had higher homocysteine concentrations than astronauts that did not have eye issues. And not only that, they had higher homocysteine concentrations in these first 3 points here, which were before flight. Now, this is one of the chemicals we looked at in the blood. We found 3 other metabolites in the pathway that were also elevated in affected astronauts. They were also elevated before flight. We brought this to the space medicine group, to the human performance group. We ruled out everything we could think of, and everything that they threw at us is, well, homocysteine is affected by a lot of things, which it is. But when we ruled out everything that we could, we started talking about the idea that genetics might alter homocysteine, genetics might alter your predisposition to these eye issues. And lo and behold, we did a study of a limited number of SNPs. And again, for a snapshot, this is the MTRR, methionine synthase reductase. The SNP is the A66G SNP. So your parents gave you 2 strands of DNA. You either got 2 A's, an A and a G, or 2 G's. Each of the symbols in here is an astronaut. And what we found is that everybody with the minor form of that SNP developed some form of eye issues. And it was 5 years ago when we trotted these data out, when this cell was empty, that people started to come around to the idea that there might be something here. My throwdown line has always been that there are a lot of people that think this is all crap and that I'm an idiot, because those are 2 different things. And when we trotted this out, I like to think that about half the people that thought this was all crap started to come around, but there's still a lot of people that don't believe this. Okay. One of the things that's, to me, is extremely intriguing is that when we looked this over, we realized that there's a clinical population that had many of the same characteristics that the affected astronauts either have or are purported to have. things like elevated homocysteine, higher incidences, SNPs. We think they have elevated intracranial pressure, but we've never been able to measure it yet. Thicker retinal neurofiber layers, altered androgens, and altered carbohydrate metabolism. We showed all those things in affected astronauts, and those things also exist in women with polycystic ovary syndrome, which is the leading cause of infertility in women, which is estimated to affect between 10 and 20% of the female population. And what we maintain is that women with polycystic ovary syndrome might just be the analog group we need to study to figure out what's different about them that might theoretically lead them to develop these eye issues if we were to send them up into space. We've since started a study with the Mayo Clinic where we're working with an endocrinologist who specializes in PCOS, a neuro-ophthalmologist who specializes in intracranial hypertension, and they're recruiting patients with PCOS and or intracranial hypertension and collecting blood and doing eye exams and sending us the samples to go off and do the genetic profiling of the one carbon pathways so that we can put this together to see if this is real. One of the more striking anecdotes I can tell you is that when we published our genetic data in the FASB journal, NASA put a blurb online about the story, which they didn't really want to do because it's hard. And the next day I got an email from a woman at one of the other NASA field centers who said, you know, what did you look at? And I sent her with a copy of the paper, and in the discussion section we broached the idea that PCOS might be this analog, and she wrote back and said, to share too much, that 6-7 years earlier she'd been diagnosed with intracranial hypertension, that there was pressure pushing on the back of her eyes that they could not figure out why, which is why it's called idiopathic intracranial hypertension. Along the way, she was diagnosed with B12 deficiency, and oh yeah, she's got PCOS. Now, is that a coincidence? It could be, but frankly, I don't think so. One of the things we were criticized then was, well, you know, we had an association between genetics and eye issues. We didn't have a mechanism, and there wasn't even a hypothesis. And I always am sort of snarkily, I'll say that it was as if we seemed to be suggesting that the DNA was pushing on the back of the eye. So we sat down with the literature and developed a hypothesis of how your genetics can lead to alterations in endothelial function that with the wrong genetics coupled with elements of spaceflight, fluid shifts, carbon dioxide exposure, a number of things that can lead to fluid pressures and alterations in blood vessel function, that you end up with decreased nitric oxide, you end up with stiffer blood vessels, which could lead to leakier blood vessels in the microvasculature in and around the optic nerve, that could block the drainage of cerebrospinal fluid out of the head, increasing pressures around the optic nerve and eye, which could lead to these problems. And we wrote that up. I sent the draft of the paper off to Jess Gregory, who was one of our collaborators on this work from the beginning. And the email we got back from him was, you need to publish this quickly. So we sent it off to the FASB journal, we published it, we made the cover, which again, when you're a dork, that's pretty exciting. And we are at the point right now where we just got some bed rest data from a study done in Germany that I can't really go into the details of, but it was just accepted for publication. And what we found was that for the first time ever, we saw optic disc edema during bed rest. Okay, and there were two things that we changed because we never do things right the first time. But the paper that we've got in press shows that your genetics drives that response. That if you had the SNPs we talk about, you developed optic disc edema, and if you didn't, you didn't. And we're very excited about that paper coming out, and we're hoping that that is what drags that last 50% of the people that think this is all crap over to our side. I remember now that they're recording this, and I probably shouldn't be saying most of what I've said, so if we could back up the recording and start over, I'd appreciate it. So that, in a nutshell, this is a time-lapse image taken out the window of space station. That's what the Earth looks like when you go by at 17,500 miles an hour, which I think is probably what this feels like, trying to cram an awful lot of work into what I hope was less than 25 minutes. For takeaway points, to state the obvious, nutrition is important for health in space and on Earth. That nutritional requirements to prevent negative effects of space travel and chronic disease must be better defined and implemented, because while we have requirements, we've never flown a food system that actually meets those requirements, and that's going to be very, very important as we move forward. Personalized nutrition, as you all know, is the future, and I've shown you one example of how that could work, because what we maintain with the eye issues is that if you were to supplement with the right vitamins and the right forms of vitamins, that you could mitigate these eye issues in astronauts. And we've proposed that, and we continue to hold our breath for them to fund some of our research. And what we, as we step back from this, I always maintain that in one way or other, literally everything we do in the space program, while it might seem somewhat trivial, and it might seem that we're spending an awful lot of time and an awful lot of money trying to keep 6 people healthy off the planet, there are implications of everything we do for terrestrial medicine, for the terrestrial population, and for just a broader understanding of how the human being works. And with that, as we approach the 50th anniversary of Neil Armstrong's walk on the moon, this is one of the pictures he took. And that's coming up next month. NASA is very excited about that. If there's any time, I would be happy to try to answer any questions. Thank you.